what today is going to give us an insight into is what I want to do next week. Okay. Now that most of you are here, I'm still going to put out a message probably later today. All right. If you have any time over the next 5 days or so, obviously preferably by next Tuesday, if you find yourself near a hobby store, okay, what you want to be doing is think about who you would like to work with. We're going to have groups of 3 for next week's little challenge, okay? But I recommend you determining who you're going to work with very soon, and then communicate with your partners, who might have an opportunity to go to hobby stores. But what I want you to pick up is this. They have like 3x3 or 4x4 or whatever. They might have different sizes. Pieces of just foam display board. Okay. Pretty inexpensive. Okay. And I think 3 pieces of that should be good. Again, this is the first year that I'm kind of ramping up the competition, where we're going to have more solid, more engineered type of airplanes. Okay. And the foam board is going to give us rigidity, and it can be manipulated into shapes. Okay. And it really doesn't need to be held together by much. Masking tape and hot glue. Okay. I need to find out how many hot glue guns we got around this school. I think we've got some. Okay. If you've got your own and wouldn't mind bringing it in, that'd be awesome too. But we're going to spend next week doing that competition. Okay. I'm going to be sending out some videos, or at least 1 or 2 videos where I got this idea from. And I've mentioned to you where I've got these ideas from, just so you can see, okay, how can I manipulate, how can I form some of this, or what kind of shapes do I want when you and your partners begin your design. Okay. And at the very end, we're going to have a competition outside to see who's playing is the best, really. Okay. So again, I'll be putting a little bit more information out there later today, but I just wanted to get those gears going so you get some ideas. And what we are kind of basing this challenge off of is the idea of fluids in motion. Okay. And so in this section, we're going to examine the motion of a fluid using the continuity equation. And we're not going to do any calculation with that. We're just going to simply explain it. We're going to recognize the effects of Bernoulli's principle on fluid motion. Has anybody heard of Bernoulli? Yeah? What do we know about Bernoulli? You raised your hand. I'm calling on you.
Wasn't his thing of fluids in motion like low pressure and things move from high to low pressure?
Sorry, say that again.
Whenever like fluids are in motion, it causes low pressure and things move from high to low. So like all the things moving.
Exactly. We also heard in the video before the chapter, I don't know if you're here for that or not, but his father was also a piece of work as well, right? He tried to steal his work and predate his published work, and it is a good holiday in that household. So let's talk about how fluids flow. Okay, we have laminar and turbulent flow. Laminar is more the smooth flow like you see in a river, where there's no obstructions, it's nice and calm. Then you get turbulent or irregular flow when you have objects, and that moving fluid has to go around that object. And when that moving fluid has to go around that object, it tends to speed up or slow down flowing liquids or gases to where you start getting turbulence, essentially. That's where the term comes from. If you're ever in an airplane, you start getting real bouncy. Okay, there's a lot of different air pressures going on in those situations. Okay. Again, these are all based off of ideal fluids, much like what we talked about in chemistry with the ideal gas, which is what we're covering now. We all base this off of situations where we assume that the fluid is behaving ideally. Okay, it's got no internal friction or viscosity, is incompressible, and it has laminar flow. And so, taking that into consideration, the whole idea of this fluid being ideal, it'll help us simplify the fluid flow analysis. And so, basically, we get this continuity equation. Okay, got to have a conservation of mass to where if we have a situation where we have fluid going from an area in, say, a pipe to an area of another of the same pipe, but is in different dimensions, basically the area and the speed in this first region has to equal the area and the speed in the second region. Okay, that's where we get that conservation of. What's happening in one has to be equal to the other. And so, depending on what the cross-sectional area of the portion where the fluid is flowing, that's going to help determine the speed. Okay, this is where Bernoulli comes into play. He says that the pressure in a fluid is going to decrease as the fluid's velocity increases. Again, that goes back to weather as well. Air is a fluid. When air is moving quickly and is warmed up, it presents a low pressure situation. Okay? And the reason why, when we go from an area that is, if you look at this cross section, we have a much larger area in this pipe here. Pressure is much greater in that pipe. In order for it to go into a narrower opening, that's a hard word to say, we have to have a decrease in pressure. So even though the water may come out faster because the fluid pressure here is greater, it has to minimize in order to essentially fit in that little space. Now, as you mentioned, Bernoulli Flight. This is where next week comes into play. Okay? This concept of fast and slow moving air. Now, if we were to take a cross section, again, it's a whole cross section idea. If we were to take a cross section of an airplane wing, okay? First of all, what does an airplane wing look like? Yes. Stand up, Ty.
What?
Stand up. We all want to see.
Yes.
Okay, it looks like arms.
Arms.
All right. So does an airplane wing look like this, where it's just kind of a flattened oval? Have you ever really seen an airplane wing in the cross section? Typically, an airplane wing looks like this. This is not to scale, okay? To where we have almost like a ridge on the upper part of the wing, okay? So this is the bottom of the wing. This is the top. As air is coming into contact with that leading edge, it's going to have to go one of two ways: over the top or under the bottom. But the key factor here is that the wind that hits the front, whether it goes to the top or bottom, if this gets split, is this direction shorter, longer, or the same as this direction? Who said it? Is going over the top longer? It is. So we've essentially, by having this form of a wing, we've increased the distance that wind has to travel. But the curious thing is that the group of, I'll call it the group of winds, the group of winds that meet here, they still have to meet back here at the tail end of the wing at the same time. So what does that mean in terms of the air that's on the top of the wing, in terms of its speed? Has to go faster to meet up with the wind that goes on the bottom. Faster air on top, lower pressure. Lower air on bottom, higher pressure. So we have a greater amount of pressure, even though it says, high pressure, greater amount of pressure here is going to allow for lift. Okay? But a lot of people have the misconception that Bernoulli's principle is the only reason why we have flight. Yeah, that's part of it. That's why I have the term incorrect theories written below there, because it's not the only thing that allows for flight. It has to come back to, our good old pal from early in the year. What do you think? Okay. 3 laws. Newton. Because the plane's wing isn't just like that. Oftentimes, again, because of this year, you really haven't been able to see my magnificent drawing skills. Oftentimes, wings are like this. They're at an angle. So yeah, we have wind hitting there, but we also have wind hitting there. How does Newton play a part in this? What do you think? How's Newton's law when we have air hitting wings at an angle? Yes. Exactly. Every reaction is going to have an equal and opposite reaction. So that wind's going to be pushing there. So essentially that wing's going to be pushing down against that wind, that air that's coming in there. And in turn, that air is also pushing it up. We have multiple factors that are occurring with flight. Okay? So let's do a few little demos here, shall we? Who would like to pass out some strips of paper?
You can do it.
Okay, thank you. Thank you. If you need more paper, I've got some.
Just one person.
One per person. Now, for fun, and obvious reasons, once you get your piece of paper, once everyone gets their piece of paper, we are going to do something. Okay? Oh, you need to participate too. All right. So, oh, thank you. Ryan, did you give yourself one?
Yeah, I gave you that one with 4. They're not on there.
Yeah, it is right.
It's not bad time. I'll personally do it.
All right. We're going to spread around the room. Okay? If you're at a lab station, you can stay there. But those of you in the seats, we're going to spread around the room because this is going to involve us. If you don't want to participate, you don't have to. Just going to leave that out there. Okay? But you're going to need your breath. Okay? So go ahead and move around. Again, if you don't want to participate, you can keep your mask on. We're only going to keep these off for a few seconds. Okay? I want you to take this piece of paper and make it float with keeping hold of your piece of paper. Can we do this? Gavin, you shaved.
I did.
Oh my goodness. Sorry. All right. So how do we do that? How do we make this piece of paper, just by holding like this, how are we going to make this float?
Blow air underneath.
You turn side. No, Ty. So let's see it. How do we do it? How do we do it? Come on, show us.
Thank you.
Oh, I see some people.
You hold on it too.
I see some people blowing it down like here. Okay. What happens if you put it underneath your mouth?
It's a lot more. Then it flaps.
It flaps. But how does blowing above it cause the air to move or cause the paper to move up?
Because it's more pressure because there's more speed below.
Because what are you doing to the air above it?
Speeding up.
We're speeding it up. So the paper that's laying like this has no other option because there's a pressure gradient. Lower pressure up top is going to cause this paper to go up like this because there's more pressure underneath. lower, slower air going underneath there. Okay. If you want to, you can keep the piece of paper and use it in other classes. I don't need it back. You all got cooties. Let's look at something else. Let's look at something else.
Oh, is it the ping pong ball and the hair dryer trick?
No, it's the hair dryer trick and the ping pong ball trick.
Oh,
Oh,
I haven't seen this one.
obviously. All right, so I've had to make adjustments to this over the last couple of years. This is my adjustment. Okay. Yeah, you gotta kind of funnel the air a little bit better. So we're gonna see if we can get this to work. I actually should have made sure that this. Okay. So if you just have it on here, I guess it works. Hasn't worked in the past. So let's see what this does. All right. All right. So why is this occurring? You have to speak up because I can't hear you.
There's pressure around it.
There's pressure around it.
Yeah.
Coming from where?
Everywhere.
Coming from everywhere. Maybe this. Right? See, there's a couple of things going on here. There's a couple different forces. Let me turn it on. There we go. A couple different forces going on. Obviously, when you have the ball up there like that, gravity wants to push it down. Okay? But the wind that is flowing upwards is also having a counteraction to gravity. So it's also going to be floating up there. And it's just enough to where, because of this ball's mass, it's not going to fall down. Okay? But we also have air that is moving relatively quickly all around this ball. So right around this ball is going to be low pressure. On the outside, where the air column is not, we've got that gradient now. So we've got higher pressure on the outside pushing in as well. That's why it's not going side to side. Then we try to see how far can we tilt it. Notice I get to a certain point, it starts to really begin to wobble. And there we go. So I was able to, with enough air or enough fluid movement to, I don't know, I'd say what was that, 45 degrees or so, roughly. But then the mass and the gravity and the amount that this can actually put out kind of lost the battle there. Okay, so that's all due to fluid motion, which creates a pressure gradient, which allows for that ping pong ball to float, allows for airplanes to fly. Okay, and is the premise of what we're doing next week. So next week, for our challenge, you have to consider some of these ideas. Okay. Do you want to have a super flat wing? Do you want to have an angled wing? Do you want to try to curve some of that foam board to where it creates a difference of heights in the wings? You know, these are all things you have to consider when you are doing engineering. Okay. So again, I'll be sending out a message later today with a little bit more specific information. Be thinking about who you want to work with, okay? And once you kind of discuss with them over the next few days, be thinking, talk to them about who might be able to go get some of the material. If there's no foam board available, shoot me an email or a message on Classroom. Let me know, and then I'll just have to make adjustments. Okay. But tomorrow is Thursday, I think. So it is review day tomorrow, and then Friday is test. Okay. Last test of the year. All right. That's a wrap for today, folks.